Hello everyone, it's Dr. Zia Tahir here, and this tutorial is about 2D beam analysis in Abaqus, and that is a beam which I'm going to show how to model it and analyze it in Abaqus. So this beam has an internal hinge. So the modeling of beams with internal hinge is different uh, compared to the others beams in Abaqus. So you can watch my these three videos: continuous beam, overhanging beam, and overhanging beam with uniformly varying load for other types of beams. So in Abaqus, beam with internal hinge, so that is modeled at two different beams or beams in two parts. Let's say this one from node 1 to 3 as left span and 3 to 4 as right span. So, and then we need to join these two beams by internal hinge. Here are step-by-step process which I'll follow to model this beam. And units, first you need to check the units. They should be consistent. And in this case, lengths, they are in meters. Loads, they are kilonewton, but I'll enter in Abaqus as newtons. And then second moment of area I have is 600 into 10 to the raised power minus 6. And I assume a square cross section. And for that one side of the beam that goes as calculated as 29.3 millimeter. So this is problem 3.3 of this book, Introduction to Finite Element Analysis using MATLAB and Abaqus. So in chapter 3, beam element, that is a problem 3.3. And here in this problem, I is given as 6,000 into 10 raised per minus 6 meter raised per 4. And I can assume that square cross section, and then side of beam comes as 291.3. So that is interface of Abaqus 2020. And before start, you need to set work directory. So you need to go file and set work directory. So default directory is temporary temporary folder in C, and I want to set that chapter 3 as work directory. So that is so now that is work directory being set. Now the first step is to create part. So for that purpose, you can use here model tree. You can use model tree or you can use that module. So when this beam need to be modeled in two parts, so 4 meter and then 4 meter two segments. So they are being here like in part. You can go there and then I'll say it as left span name 2D deformable wire and the approximate size. Approximate size is almost two times the uh, total length of the beam. So it's 14. So I am going to go for let's say 30. So continue and then here connected lines. So starting from origin, that is the first span of 4 and then another span of 4 and then cancel procedure. Once you have drawn it, so it's done. And now you can see in the model tree, so left span has been modeled. Now then you will now click in the model tree, click on parts. So now it is right span, 2D deformable wire, approximate size 30. So I'm going to continue here. The previous part, like left span, I started from origin, and then this one I am going to start, let's say, from here. and then its length is 6. Okay, so that span is being drawn, then cancel procedure and done. And now you have here in the model tree or even in the part module, you have left span and you have right span. Next step in the property module, you need to create material. And the material for this beam is steel with modulus of elasticity 200 gigapascal and Poisson's ratio is 0.3. So you can go here property module and you can create material here, or otherwise in the model tree you double click on that material. So here create material. So material name is steel, and then description you can put that, and material behavior you can put, but I'm going here mechanical elasticity and then elastic. And modulus of elasticity as 200 e raised per 9 or 200 gigapascal, and Poisson's ratio is 0.3. So that is now material is being created. You can see here, and even you can see here that the material is being created. Step is you need to create profile, and the profile I assumed here as square cross section, and which is each side as 0.2913. So I'll go here. So in the property module, you can create here profile, or otherwise in a model tree here you can profile. So you can double click here or you can double click here to create profile. So profile, let's say, is square, and then it doesn't have option of square, so you will select rectangular, continue, and A and B is 0.2913. Okay, so these are, now you have created profile. So the next step is, after creating profile, you need to create section. So for create section, you can go here property module, you have create section here or you have sections there. So you can double click on that here, or just click on that and section. So it is beam section, let's say, and category is beam and type is beam. So continue, and now it will get square and the material is steel. So I click OK. Next step is assign section. So for assign section, you need to go to part, sorry, in the property module, you need to assign section. So here you have assign section. So don't need, you don't need to create a set for that. Now you have two span, right span and left span. I just first click on right span and then assign section. It's a select the region to be assigned local. So that is done. So then it's the beam section, and for right span, assign section, and then you'll have here done. Okay. Now the sections have. Next step is in property module, you need to assign beam orientation, and for that purpose, you go property module and then left span first, and then you have here assign beam orientation. So select the region to be assigned a beam orientation. So I'll click select it, done, and then these are the default value you leave as it is, and then OK, and that is done. Now in the property module, you need to go to right span, and then for right span you need to assign beam section, that is selected, then press enter and OK. So done. So beam section orientation has been assigned. Now the next one is assembly. In next step is assembly, and you need to create instance. So you can go here using assembly module, or you can go there and then in assembly module, you can create instance. Let's see here. It's a create instance from the part. So I select both ones and then I said okay, and you can see that two instance has been created, left span one and right span one. So now the next step is we need to join these two so that a hinge is being created. So to create hinge, actually that is a left span and that is right span. So we need to join those two by a hinge. And the step is you need to go interaction. So now in the interaction module, you need to create wire feature, create connector section, and create connector assignment. So for that one, you need to go interaction. So in the interaction, you need to create wire feature. So it says that geometry type polyline and disjoint wires. So from here, you need to add a wire. Okay, and it says that the select first point. So that is the first point, and second, that is the second point, and then done. So now, because you want to connect left and right uh, span, and that is a wire you have created, so you can join that. So, okay, so now that wire has been created. And the next step is you need to go again interaction, create connector section. And in interaction, you are already there. And here you can see that create connector section. So for connector section, it is connection category is basic for this type of hinge. Translational type, like translation is join. So if they are going to move, so and rotational type is rotation. So for a simple plastic hinge, you need to select category basic, translation is join, and then rotation type is rotation, and you need to continue. Okay, and then here you behavior option, I click here add elasticity, and this is a rigid joint. So rigid, and then you need to check here UR1 because we are modeling a 2D beam, and in 2D beam along x-axis there is no rotation, so that I have checked, and then I click OK. So next one, you have created connector section. Now you need to next step here is create connector assignment. So for that one, again, interaction. And here you have connector assignment. So I click on that. It says select wire or attachment line to assign section. So this wire I'm going to select. Done. And connector section is already I have defined. So I select OK. So now that interaction has been defined. Now, the next step after that is you need to translate instance in assembly. So you need to move that uh, left span to right span. And for that purpose, you need to go to assembly, and here you have different option. It's a translate instance, translate to, and then rotate. So I'll go for translate instance because I want to move that in along X or Y axis. So I click here, it says select the instance to translate. I want to move that left span, and it says that done. It says select an axis or a start point of translation. So that is a start point of translation, and I want to move that here, and that is end point. Okay, so done. Okay, and now that part has been translated. So now the total length of the beam, that is the left span and that is the right span, and you say done. To check that, I'll go in the part module. Okay, so you can or you can go here in the assembly module to check that. So that is left span and that is right span. So now in between both of you, both of these, here is a plastic hinge. So now plastic hinge has been created. So now the next step is I need to I need to mesh that. And before that, because if you see there, so you left span, so mesh is empty, and right span mesh is empty. So I'll go in assembly instance and I right click on left span and I say it as make independent. And then before you can see that mesh was there and now mesh has been moved there. And then right span, you can see mesh here. And if I click on right span, double right click and then make independent. So now you can see that mesh comes there. So now previously, now you need to mesh that one. So go to mesh module and here are the steps for mesh. Seed, mesh part, assign element type. So in mesh, it's a you have option. So model one, then assembly, and then part. So you can mesh these two parts separately, or you click on assembly, and in assembly, you can mesh both parts at the same time. So now I clicked on assembly, and here is seed edges. So I select that one, is done, and by number, oh sorry, by size, I'm going to set as 0.5 meter. So apply, and you can see that. So here you have nodes as squares and then the other all elements. So it's done. Next one, you need to go here, mesh part instance. So mesh part, it says select the part instance to be meshed. So you can see there is one part here, one part there. So I'm going to select both parts and then done. It say select the part. So it's done now. And you can see there. So you have mesh here for both spans. And then you need to assign element type. So select the region to be assigned element type. I'll select all that. Done. And then standard linear and in a family beam. So I click on that. So D2, 1 and 2 node linear beam in plane that is being selected. So that is done. So now you mesh that. Next step is you need to create step. So for that purpose, you can go into the module and you can have step there, or you can use in the model tree. You can use in the model tree step there. Okay, so either there or here. So I create step. So that is static load, and then initial procedure type is journal, static journal, continue, and then leave everything as it is. So now you have created a static load. Now the next step is you need to create boundary conditions. Okay, so the boundary conditions are like on the left side it is a fixed port and on the right side it is a fixed port. So I'll go to the boundary conditions and it's step initial and I am going to left fix. Okay, I name it and then displacement rotation, continue, and then select the region for boundary condition. So that is the point. So it's done. And then at fixed ports, all these uh, displacements are zero. So I click OK. And you can see here is a left fix. Now again, it is right fix, mechanical displacement rotation, continue. And there you are. And again, you need to fix all those. Okay. Now you need to make sure that that is step is initial for both of sports. Now the next one is loads. You need to apply loads and the load is 12 kilonewton at 4 meter. and then I'll go load and name I can as a point load initial. Here I'll go static load because I have defined this mechanical category and concentrated force continue, and I'm going to apply here at 4 meter done, and CF2 it means that is a vertical direction, so minus 12 e raised per 3 minus 12 kilonewton is the load. So I click OK. So now model has been created. So the model or beam with hinge has been created. So now the next step, okay, so I'm going to name that model. So rename that, and I'm saying it as chapter 3, and then it is problem 3.3. So that is the model. So okay, so now that is the model, and I'm going to save it, file, save, and this one CAE file is being saved as chapter 3, problem 3.3. Okay, so it is being saved in the work directory, which is chapter 3. So now this model has been created, model renamed and saved. Now the next step is you need to perform analysis, and for that one you need to go job and create job. So now you can go here, job, and you can click here to create job, or otherwise you can go here jobs, double click that, and the job name I am saying it as chapter 3, problem 3.3, continue. Oh, it says that. So it can't use space. You can't use space for the jobs. Okay, so continue, leave everything okay. And now you have that job, or otherwise you can go here, okay, and you can click on data check, okay, and you can see that check submitted, check running, and then after some time, check completed. So that is check completed. So if check completed and is not being aborted, like it doesn't show any error, so then you need to submit it. So right click here and you can submit, or from here you can submit it. So right click here, submit, and then it says that job file already exists for that one. So okay to override. The job is being submitted, running, and then when it's running, it takes some time to complete. So it is completed. So now I can check results, because the last step here is results. So you can use visualization module for common. So it is being right click on that and go to the results. And now you can see in the result tab, output database, you'll have that chapter 3, problem 3.3 ODB. That is the one way, or otherwise you will go file, open, and you select here ODB, and you have here chapter 3, problem 3.3 ODB. So now it is being opened. So now that is the beam in undeformed shape, and that is deformed shape. So if you want to view the nodes here, so you can go here, common options, and then you can go to labels. So show node labels, apply, and you can see there it is first node there, second node here, that is the third node there, and for this part that is the first node for left span, and it goes up to 13. Okay, and then if you want to go for contour plots, so these are the contour plots. I am unchecking that node labels. So you can see von Mises stresses. You can go for like displacement in magnitude or UR2. So that is, you can visualize your result. So now if you want to create a report file for that, so you can go to report tab and you can select field output. So here you can go here report, field output. And in field output, you have variables. So we are looking for unique node. And that at that unique node, I want to plot that U2, you are 3, or you can just click on that. So spatial displacement. So it's being selected. Then you can go for any other of your choice. So let's say I just want to create a report for these displacements. So I'll go setup and then I name it as chapter 3, problem 3.3. Okay, and I'll apply it. So once it's being applied, so in your work directory, a report has been created. Here is the report, and in that report, you'll have that node labels for part one. It is for the left one, so it is being created for only part one. So here is chapter 3, problem 3.3 report. So now you'll have that for left span and then for right span. So there are two files created. So for left span, that are the nodes from 1 to 17, and for the right span for node 1 to 13. And then you can compare those results with theoretical results, or you can compare with FEA results. So that is all about modeling, then performing analysis, and then visualization of results of a beam with internal hinge or plastic hinge in Abaqus. I hope that this video is useful for you, so you can leave comments for your feedback. Thank you very much for watching.